Hey there, this is Mathcamp321, and this is a video on solving exponential equations using the common base method. Before we actually get to the common base method, we're going to do a warm-up exercise in which we're asked to rewrite each value in the form of a to the power of b, where a is the smallest integer possible. We'll do number 64 together, and then I'd like you to pause the video and try the rest on your own before I reveal the answers. When I look at the value of 64, there's actually a few different options that come to mind. It could be 8 squared, but it also could be 4 cubed, and there's actually a third option, and that would be 2 to the power of 6. In the directions, we're looking for the base that is the smallest integer possible. So when I'm choosing between an 8, a 4, and a 2, the 2 is going to be the winner. So 2 to the power of 6 is going to be the combination of a to the power of b that I want. So at this time, I'd like you to pause the video and try b through I, and then resume the video where I'll reveal the solutions to you. Okay, I hope you took a moment to actually try the problems. The value 625 that we see in letter B can be thought of as 5 to the power of 4. In C, we have the value 1000. This can be thought of as 10 cubed. D is a little bit tricky with the value 1/9. This is going to require a negative exponent. I'm going to perceive this as 3 to the power of -2. If you had just written 3 squared, then the answer would have been 9. In order to get that 9 into the denominator, we're going to need a negative exponent. So that's why the answer is 3 to the -2. In letter E, the given value is 0.1, or as a fraction, 1/10. Again, since the action's in the denominator, we're going to need a negative exponent, and this is going to be 10 to the -1st power. In letter F, we're dealing with the fraction 1/27. Now, I know that 3 cubed is 27, so to get the 27 in the denominator, it's going to be an answer of 3 to the -3rd. In letter G, we have the value 8, which can be thought of as 2 cubed. In letter H, we have the fraction 1/16. Now, 16 is a tough one because there's a few options. You can think of 16 as 4 squared, but if we're striving for the smallest base possible, you actually really need to think about it as 2 to the power of 4. But since the 16 is in the denominator, the answer is actually 2 to the -4th power. And finally, we have the decimal 0.01, which is the same as the fraction 1/100th, which in this case will give us an equivalent a to the power of b of 10 to the -2. So let me take a moment to box in these final answers, but this warm-up is going to be really helpful in solving exponential equations using what's called the common base method. Okay, great. Let's move on to the next slide. On this slide, there's a rule that is revealed to us that says if x to the power of a equals x to the power of b, then a must equal b. In words, if two exponential expressions are equal and have the same base, then their exponents must also be equal. Examples: solve each exponential equation using what's called the common base method. As we look at number 1, it says 5 to the power of x minus 1 equals 5. So in this problem, we have exponential expressions on either side, and we already have a common base. There's a 5 on the left, and there's a 5 on the right. Now, the left has a power of x minus 1, and on the right there is no power, but we know that there is an implied power of 1. 5 is really 5 to the power of 1. I'm going to go ahead and write that 1 in, so it's really obvious. Now, according to the rule above, if you have this situation where the bases are the same, merely equate the exponents. So this generates a new equation of x minus 1 equals 1. Adding 1 to both sides, we end up getting x equals 2. If we do a check, by plugging that x value of 2 into our original question, we get 5 to the 2 minus 1 equals 5. And of course, 2 minus 1 is just 1. And we know that 5 to the power of 1 equals 5. So of course, this does check out. Let's move to example 2, which says 2 to the power of 3x plus 1 equals 4. Now in this problem, we have a base of 2 on the left, and we have a base of 4 on the right. So we're striving for common bases, and in this problem we don't quite have that. So I'm focusing my attention to start on the right-hand side, and I'm hoping to replace 4 with perhaps a base of 2 because that's the base on the left side. And I know 4 can be rewritten as 2 squared. So my next step will be to write 2 to the power of 3x plus 1 equals 2 squared. Now that we have common bases to the left and right sides, I can merely equate the exponents together, yielding the new equation 3x plus 1 equals 2. Subtracting 1 from each side, I end up with 3x equals 1, and dividing each side by 3, I get a final answer of x equals 1/3. Now I'm going to do the check one more time with you, but after that, it's something that I expect that you'll do on your own. Plugging 1/3 into the original problem, we end up getting 2 to the power of 3 times 1/3 plus 1 equals 4. 3 times 1/3 is 1, and 1 plus 1 is 2. And 2 squared, of course, equals 4, so this answer also checks out. Let's move to the next slide. In example 3, we're asked to solve 3 to the power of 5 minus x equals 1/9. Again, we notice that there aren't common bases. Is it possible for me to get common bases? Well, I think I can do that if I replace 1/9 with 3 to the negative second power. In writing the problem that way, I now have common bases, and I can simply equate the exponents. 5 minus x equals negative 2. Subtracting 5 from both sides, I get negative x equals negative 7, and finally that x equals 7. Again, I'm going to leave the check up to you, and it's something that you should do until you're absolutely confident with the process. In number 4, we're asked to solve 8 to the power of x squared is equal to 16 to the power of x. Now this is tough. There certainly are not common bases to start, so it's going to require thinking about what we have and asking ourselves, is there a base that's common to both 8 and 16? And the answer is there is, and that's the base of 2. If I replace 8 with 2 cubed, and I replace 16 with 2 to the 4th, then I think I'm going to be good to go. So that's how I'm going to start. Now, a rule of exponents is creeping its way in, and that rule is raising an existing power to a new power, which happens in both of these sides of the equation. So recall that when you're raising a power to a new power, you're going to multiply. 3 times x squared is 3x squared, and 4 times x is 4x. So we're going to get 2 to the 3x squared equals 2 to the 4x. Now that we have bases that are common to both sides, we can simply equate the exponents. 3x squared is equal to 4x. Because this is a quadratic equation, my next maneuver will be to set the whole thing equal to 0. 3x squared minus 4x equals 0. I'll factor out an x because it's the greatest common factor to both terms. And setting each factor equal to 0, I end up with x equals 0 and 3x minus 4 equals 0. Well, x equals 0 is done, so I'm going to put a box around that, but I've got a little bit more isolating to do with the second equation. Adding 4 to both sides, we get 3x equals 4, and we conclude with a final answer of 4/3. Now, do you think it's the case that one or both of these answers don't work? The only way you're going to know is if you check. That's how you're going to become a very confident solver of problems using the common base method. Let's go to the next slide. In example 5, we're asked to solve 1/27th to the power of 5 minus 2x equals 1/81st to the power of x plus 6. It's obvious that we don't have common bases, but can we think of a base that would be common to both 27 and 81? And I think there is, and that would be the base of 3. I'm going to replace 1/27th with 3 to the negative 3rd power, and I'm going to replace 1/81st with 3 to the negative 4th power. Remembering that when you raise a power to a new power, you multiply, we're going to distribute the negative 3 through on the left side and the negative 4 through on the right side. So we're going to end up getting 3 to the negative 15 plus 6x equals 3 to the negative 4x minus 24. Now that we have our common bases on each side, I can simply equate the exponents. I'll start by adding 4x to both sides. Next, I'll add 15 to both sides. Finally, I'll divide by 10. So for this problem, I'm getting a final answer of -9/10. And of course, your job should be to check this. In number 6, we're asked to solve 125 to the power of x squared plus 1 is equal to 1/25 to the power of 5x. Again, we don't have common bases, but we need to find the common base, and I think in this case it's going to be the number 5. If that's what you were thinking, then you're correct. So I'm going to replace 125 with 5 cubed, and I'm going to replace 1/25 with 5 to the -2nd power. Again, when raising a power to a new power, we multiply, so now we're going to get 5 to the 3x squared plus 3 is equal to 5 to the -10x. Because we now have common bases to both sides, I can simply equate the exponents. Because the result is a quadratic, I'll now set everything equal to 0. Since 3 times 3 is 9, and the factors of 9 are 1 and 9, which give you a 10, I know this is factorable. Our two factors end up being 3x plus 1 and x plus 3. Setting each of these factors equal to 0, I get the two answers of x equals -1/3, x equals -3. And again, I would highly recommend that you check, especially when you're learning something, to really get the sense that you know what you're doing and build your self-confidence. So in this video, we learned how to solve exponential equations using a method called the common base method, and it's all about rewriting each side of the equation if necessary so that you get common bases.